Well, welcome everyone. This is going to be 3 lectures just to get us started in computational astrophysics. So I'm going to call these 3 lectures a crash course in compressible fluid dynamics. And the reason we need a crash course is before we go doing anything on the computer, we need to understand what it is we're trying to do and what equations we're trying to solve. So I'm going to give you a quick introduction to compressible hydrodynamics. And it's going to be a bit of a whirlwind tour because we're really going to focus on the computational aspects in this course. So I'm really going to give you like some very basic physics and maths overview. Just basically the essentials that you need to get going. So let's start with compressible hydrodynamics. So what do we mean by compressible hydrodynamics? Well, so by hydrodynamics, we mean a particular set of partial differential equations. So what we mean is a set of equations. So the equations of compressible hydrodynamics, compressible hydrodynamics. And these are the inviscid equations. They're also called the Euler equations. So if you had viscosity, these would be called the Navier-Stokes equations. But Navier-Stokes equations are usually used in incompressible flow. And we're going to deal in astrophysical fluid dynamics entirely with compressible flow. So essentially these equations are simply mathematical expressions of physical rules. And those physical rules are pretty simple. So our physical rules are simply the ones you know and love from a lot of physics. They simply express the conservation of mass. So this is what you call the continuity equation. So this is the continuity equation. And it expresses the conservation of mass. So rho is the density, v is the velocity. This is our divergence operator. We're using vector notation. So the second you can probably guess. It expresses, now we're writing these, this is velocity, so it's acceleration per unit mass, v dot grad v. Equals minus a pressure gradient divided by density plus any kind of external accelerations. This is our momentum equation. And it expresses, obviously, conservation of momentum. And when we say a fluid could be a solid, a liquid, or a gas. Usually we're going to refer to gases because we're thinking about astrophysics, so we don't have many liquids in space. So this is the internal energy per unit mass, or the thermal energy. And the equation for the internal energy per unit mass is du dt plus v dot grad u equals p minus p on rho divergence of the velocity plus, well, heating and cooling terms. So you can think about that as a heating term minus lambda cool. So this is our energy equation. I'll try not to run off the board this time. So this is our energy equation. And it expresses conservation of energy. So we got, well, how many equations are there is a good question. So this is a scalar equation. There's 3 equations here for conservation of momentum because there's a vector equation and another scalar equation, but they're expressing 3 basic rules. We want the universe to conserve mass, or we want our little experimental universe to conserve mass. We want our system to conserve momentum, and we want our system to conserve energy. Now you'll notice already in these 2 equations that these terms look very, very similar. The only thing that's changed is the variable here. And that's no accident, simply because it expresses the physics of moving. So the physics of moving is called advection. And so these terms are advection terms. And they don't really, well, it's just literally the physics of picking something up and moving it around. And that's how we express advection mathematically. So I'm going to shorten these equations a little bit with a little bit of notation. And especially because we're going to consider Lagrangian methods later in this course, we can simplify these equations by defining something called a co-moving derivative. All right, so while I rub this out, just going to take a while. This is my first experience on the light board, so excuse me if I'm a bit slow rubbing things out. Incidentally, my name's Daniel Price. I'm an associate professor here at Monash, and I work in computational astrophysics, in fluid dynamics in particular. All right, so we can simplify these expressions by using what we call the co-moving time derivative. So the co-moving time derivative, and hopefully you've come across this in your undergraduate studies. So the co-moving time derivative, I'm going to use just a Roman ddt here. And the definition is that it's the partial time derivative plus v dot grad. And it's an operator, so it's an operator. So for example, if you put a density here, you put a density here and a density here. So you can see that that would capture our left-hand side of our equations into this single time derivative. Now the way to understand the co-moving time derivative is, this is the time derivative. So it's the time derivative for a co-moving observer. What does that mean? It's the time derivative such that the time derivative of position equals velocity. So we're thinking of, it's a kind of Lagrangian quantity, so it's really, when you're moving things around with a velocity v, this is the rate at which your position changes. Now it doesn't really ever make sense to do something like a partial time derivative here. That doesn't make any sense. So this total time derivative is the one we mean when we say, when you move something with a speed v, this is the speed on which, this is the time derivative for if you're sitting on that blob, how the quantities on that blob change with time. So for example, so our compressible fluid equations become d rho dt. Now this is on the exercise sheet for you to just prove these things yourself. It's not very difficult. So what we had is a divergence of rho times velocity. That becomes expanded into two terms of v dot grad rho, and that comes on the left-hand side and gives us the total time derivative. And you'll notice already in our momentum equation that we had a dv dt plus v dot grad, and that becomes a total dv dt. So this gives us a minus grad p on rho, so the right-hand side is still the same as before, external accelerations or body forces. And we have our du dt equals minus p on rho divergence of velocity plus any heating and cooling terms. So while you may not be very familiar with these kind of different time derivatives, again the way to understand it is, imagine you've got a river and you've got a boat on the river. Here's a boat and it's traveling with some speed v. Now imagine you're trying to work out the density of boats, for example. So the density of boats is simply 1 when there is a boat and 0 when there's not a boat. So here, the time derivative, if we're an observer sitting on the bank, our time derivative would be the partial time derivative. We would say there's no boat, so the density is 0. The boat comes into view, so the density is 1. The boat goes out of view, so the density drops back to 0 again. So the time derivative for this observer would be the partial d boat dt, or boat density dt, whereas now we consider observer sitting on the boat. Its density of boats is always a constant, so we would say db dt with the total derivative equals 0. Okay, but this ddt captures the fact that this boat is moving, but we have to treat that as a separate equation. All right, so that's what this total time derivative means. And we're going to come back to that. But there's a problem here. So this is our set of equations. These are our equations of compressible hydrodynamics. But I wonder if you've spotted something wrong with these equations, which is, well, what we'd like to do is solve them. And can we solve them is the next question. So let's think about what we have here. We've got density, we've got 3 velocities, and we've got a thermal energy. So that's 1, 2, 3, 4, 5 quantities in 3 dimensions. And we have 1, 2, and we've got a pressure as well. So that's 5, 6 quantities. We have 1, 2, 3, 4, 5 equations. All right, so we've got 5 equations for 6 unknowns. And so we need what's called a closure relation in order to solve these equations. And that closure relation is called the equation of state. All right, so let's cover the equation of state. So what we are missing is the equation of state. So we have 5 equations for 6 unknowns. And we close with an equation of state. So we simply need to relate one of these quantities to any or all of the other quantities. So the equation of state is a quantity that is an equation that relates pressure to the thermodynamic variables U, so the thermal energy or the temperature and the density. So for example, the most common would be the ideal gas equation of state. So I'm going to just cover some details on that and how we use it usually in fluid dynamics. So hopefully some of this is just revision for you, but if not, then hopefully it all makes sense. So for example, for an ideal gas, we would use pressure equals rho kBT on mu mh, where mu is the mean molecular weight, that's the Boltzmann constant, T is the temperature, rho is the density, and mass is the mass of a hydrogen atom. Now, just for astrophysics, I would always recommend using the ideal equation of state in this form. In particular, using things like R get horribly confusing. We never deal with moles in astrophysics. So I would always just recommend, I mean, this is just a combination of constants. Mu is basically, 2 if you're molecular hydrogen, 1 if you're atomic hydrogen, and depending whether you're ionized or not. So it's the mean weight per molecule. Kb is just a constant, mh is just a constant. So I would recommend using this form of your ideal gas equation of state just so you don't get confused. Now, what we usually observe is the temperature, but this equation also has the composition in it. And so it's more helpful usually, so mathematically we'd actually couldn't tell the difference between a change in temperature and a change in composition. If you increase temperature by a factor of 2 and the mean molecular weight by a factor of 2, it would have exactly the same pressure. And if you remember, our equations only contain the pressure gradient. It doesn't contain U or T directly on the right-hand side. So what we do is we use the internal energy, which I've already written down for you, instead of the temperature, because it means we don't need to worry about the composition. If we do that, it means we don't need to worry about the composition, about mu. Well, we only need to specify a mu when we want to interpret our results in terms of a temperature. So what we simply write is P equals gamma minus 1 rho U as our equation of state, where gamma is the ratio of specific heats. So this is sometimes called the adiabatic equation of state. And that implies that gamma minus 1 U equals or is equivalent to saying that's equal to kBt on mu mh. So these two expressions are equivalent, but we just prefer using this one because this gives us our pressure in terms of our density and internal energy, and we never really have to worry about what the temperature is. Now, if the composition's changing, in general, this could get complicated. For example, we might have a more complicated equation of state. This equation would still hold, but we'd have to do something complicated by looking up, for example, the temperature from the internal energy. This gamma is sometimes not a constant. All right, but for most simple fluid dynamics problems, we can simply use this equation as our equation of state and specify what gamma is. All right, so I want to show you one little trick already. So we've got our P equals gamma minus 1 rho u. But we can simplify this. So if there is no heating and cooling, we can actually get rid of our energy equation and we don't need to solve it. And I'll show you what that looks like. And you're going to do this later in the course as well. So a simpler equation of state, so EOS for equation of state here, can be used in the case where there is no heating and cooling. What do I mean? So in particular, if we take our du dt equation, this is our energy equation. Remember, that's minus a p on rho divergence of velocity. But if you remember, so recall that d rho dt equals minus rho div v. And so this is simply, now we've dropped our heating and cooling terms here, so this is all the terms we have in this equation if there's no heating and cooling. So this simply gives us a p on rho squared d rho dt. All right, but now if we then use our equation of state, p equals gamma minus 1 rho u, then what do we get? Well, let's see. So hopefully you can see this is now just a separable differential equation. And so we can have simply 1 on u du dt equals a gamma minus 1 on rho d rho dt. All right, so in other words, we get a d log u equals d log rho to the gamma minus 1. So if you're not clear on that, so that's a gamma minus 1 d log rho, and then I've just the gamma, when you take it inside a log, it becomes a power, the gamma minus 1. So then we can just integrate both sides. And we obtain simply that log u equals log rho to the gamma minus 1 plus a constant. Or in other words, that therefore that u is some constant, which I'm going to call k tilde, rho to the gamma minus 1. And therefore that our pressure, so pressure is gamma minus 1, but gamma is a constant, rho times u. And so that means that pressure is some different constant, which I'll call k, rho to the gamma. So that's what you call a polytropic equation of state, which is simply that P is proportional to rho to some power. So in particular, so this is called a polytropic equation of state. And it's equivalent to saying we are adiabatic, that's our adiabatic equation of state, with no heating and cooling. So if we had no heating and cooling, this is equivalent to taking our energy equation with this equation of state, then we can get this as the solution. And so in that case, we can actually just drop one of our equations from the set, and we only have to solve the momentum and continuity equation. So that's very helpful in a lot of computational work where you can make a much simpler approximation. if you understand the thermodynamics. And also, so I just want to give you one other example. So the isothermal equation of state. So the case gamma equals 1 gives P is proportional to rho. All right, so if you take gamma 1 here, you just get P proportional to rho. And, well, if you recall from our P equals rho kBT on mu mh, now kb, mh, and mu are all constants, this implies that a T equals constant. So gamma equals 1 is what you call an isothermal equation of state because it implies that temperature is a constant. And in that case, we would call this constant the sound speed squared. And the reason for that is not clear yet, but we're going to come to that in just a second. All right, so that's the basics of our equation set, and I might just recap them for you. So we've got our conservation of mass, conservation of momentum, conservation of energy, and we've got an equation of state which closes our equation of state. And so we can take simpler equations of state that can drop our energy equation. So a lot of the time we don't actually need to solve the energy equation at all. But in the most general case we would need to. But the question is, well, how do we discover some of the physics of these equations? So that's the basic mathematics of it. So how can we discover the physics of these equations? I mean, what do they mean? What sort of solutions might they hold? So I want to come to this, and I'm going to give you the physicist's view. There's a very mathematical course on this. I once taught an entire 8 lectures on parabolic partial differential equations. It was not the most fascinating lectures. So I'm going to give you the physicist's view of how you can understand what's in a set of equations. All right. It keeps you fit, this kind of erasing the board. So I'm going to call this section, so what is the physics? What is the basic physics in this set of equations? Now, I don't know if you've taken a partial differential equations course yet. Hopefully you have by the time you get here. But even if you haven't, I can give you just a real quick crash course in partial differential equations. So essentially, PDEs are classified into 3 basic types. And I'm not even going to give you the mathematical definition. You can look it up. It's to do with the coefficients in front of the second derivative. So a partial differential equation is an equation expressed in at least 2 variables. So for example, time and space. So the 3 basic types, so they are elliptic, hyperbolic, and parabolic. But there's kind of a prototype equation for each kind, and you should be able to, and they represent different kinds of physics. So for example, here is an elliptic equation, 4 pi g rho, and if you've done your undergraduate properly, you should recognize this equation. It's Poisson's equation for the gravitational field from the mass distribution. Now that is an elliptic equation. And how can I tell? Well, there's no time. So this is a purely spatial derivative. So partial differential equations, we usually have second derivatives of something. So we have a second derivative of the gravitational potential, but there's no time involved in this equation. And that means that the gravitational potential everywhere is known as soon as you change the density anywhere in the space. I mean, this is what we get from Newton's law of gravity. We get what we call instant action. So elliptic equations are characterized by having instant action. And numerically, that means that you have to do something special because you need to propagate the information. So imagine you have some grid, for example, and you change the mass over here, it means that every other grid cell in this box needs to feel a change in gravitational potential in one time step. So you have to do, so the special thing about numerical methods for solving elliptical equations is you have to do a global propagation of the information. So the information has to be spread across all of the cells. All right, so the second kind of equation is typified. So the example is what we call the heat equation, kappa del squared U. So du dt is kappa del squared U. And, well, if you were here live with me, I'd say, what's the physics in this equation? So that's what you call a parabolic equation. And I can tell you without going into the mathematical definition by looking just at the physics of it. So again, the mathematical definition is to do with, how many kinds of each derivative I have. So you can notice here I have just a single spatial derivative, whereas here I have a spatial second derivative, but only a first time derivative. Another way of looking at it is in terms of dimensional analysis. So there's a coefficient here, so my kind of constant here, this kappa. So this kappa in my heat equation, so just looking at this, so my dimensions on the left here, I have a u divided by a time. And on the right here, I have a u divided by a length squared. So therefore, the dimensions of this thing must be a length squared per unit time. So the dimensions of kappa must be an area per unit time. And when you're doing this numerically, that must mean that you're going to have a time step, which is something like the spatial resolution length divided by kappa. And in the elliptic equation, this time step is, who knows? Well, actually it's instant, so there's nothing to do with time in the equation, so I don't have to take any steps in time. It's just a spatial propagation of information. Whereas in the parabolic equation, I've got this, what I call a diffusion process. And diffusion is tricky because, well, I can end up with very fast timescales. So it's somewhere in between instant action and hyperbolic, which I'm going to come to next. Because it has different timescales for propagation on different length scales. So for example, very short length scales give a very short time for propagation, whereas long times take a very long time to propagate. All right, and the final sort of typical equation is what you call a hyperbolic equation. So this is typified by this equation, which you may be familiar with, minus del squared u equals 0. So I've put that on the left-hand side just because that's normally the way you'd see things. So again, here we've got a second spatial derivative and a second time derivative. And this is what you would call a hyperbolic equation. And the physics of that equation is what you call waves. And this c in this equation, so this is just the wave equation, so this is the heat equation, this is the wave equation, and this is Poisson's equation. And the physics in this equation is that information propagates as waves. And that means that, so for example, the dimensions of c are just a length scale per unit time, so it's a speed. It's the speed at which my waves propagate. And my time scale is going to be of order the resolution length, delta x, divided by the speed. Sorry, I've gone off the end of the board here. So my time scale here would be the delta x divided by the speed. And my time scale for the heat equation would be something like a delta x squared on kappa. And the time scale for my elliptic equation is, well, nothing. All right, so that's how you classify partial differential equations. And I just wrote down on the board a few minutes ago a set of partial differential equations. So the question is, what kind of equations are the Euler equations? And, well, I don't know because I've got a set of equations. I don't have anything that looks like one of these equations. So it's not easy just to read it off what I've just done. So instead, we're going to do a little bit of work. All right, see you in a minute.